Okay, we're on page 17. Page 17. We're going to come back to the rational zeros theorem. So the theorem says if you have a function where that function is a polynomial, then if you have no way of factoring, you just don't know what the factors are, you can start guessing what the possible zeros are. Now, what you need to do is you want to have educated guess. So that comes from these two numbers. The leading coefficient and then the last constant of your polynomial. And what you're going to do is look at the last constant first. That constant, what you're looking for is the plus minus p or plus minus of the factors that make up that constant. Okay, we call that number p. And then we look at the leading coefficient, and then we do the same thing. We look at the plus minus factors, which we call a q. Eunice is shaking her head because she knows what's coming. This is the plus minus p plus minus q. So the possible rational factors are plus minus p over q. So, this is what we did last year. It took a long time. So plus minus p over q is the possible rational factors of f of x. Now, it says it's possible because not all of them will work, or maybe none of them will work. But let's try it. Okay, so for example, let's look at this one. Before you do anything, it says it wants the rational zeros. So basically, it doesn't want the imaginary zeros. So only rational zeros. Review rational numbers. What does rational numbers mean? Give me an example of rational number. Huh? 2. Yes, 2. What's another number that's rational? 2.3 repeated. Yes. Okay, so basically anything you can make into a fraction is a rational number because the word ratio. Okay, fraction. So anything you can make into a fraction is a rational zero. Rational number. So they don't want irrational zeros, like square root 2. They don't want imaginary numbers, only rational zeros. All right, before you do anything, you always ask yourself, can I factor? Yes? No? Can you factor as is? No. Can you use quadratic formula? No. Okay, you cannot because it's not quadratic, it's cubic. So before you do anything, you always want to ask, can I use an easy method to solve this? No, you cannot. So you have to do p over q. So what you're going to do is find the plus minus p factors. All right, plus minus p factors has to do with the constant. What are the factors of 1? 1. Okay, that was easy. So it's going to be plus minus 1. Because we always have the plus minus of it. Okay, plus minus q has to do with the leading coefficient. What is the leading coefficient? 1. So then what's the plus minus version of the factors? Yeah, plus minus 1. So plus minus p over q is really easy. Plus minus 1. So there are only 2 possible rational zeros. It's either 1 or negative 1. So we're going to check. Let's say you check 1. What's the fastest way of checking whether 1 is the zero? Yeah?
When you put it in the thing and see if the remainder is 0?
Yes, the remainder is 0. So if you plug 1 into the function and you get 0, then that is the 0 of the function. So that would be the fastest way. We have 2 numbers, 1 and negative 1, so we're just going to check both. If you get 0, that is the 0 of the function. So go ahead and try it. F of 1 is equal to what? Minus 1. And then f of negative 1? Negative 3. So are they zeros? No. What does that mean? Are there no zeros in this whole function? That's not possible, right? It tells us there are 3 zeros. So what does that mean? Huh?
Maybe they're imaginary.
Maybe they're imaginary or not rational. Yeah, so basically whatever it is, they're not rational zeros. So this theorem just tells us that there's no rational zeros in this function, but there are 3 zeros of some other kind. Okay? All right, let's try another one. Sorry. Here's the practice. Ugh. Okay, find all the rational zeros of this function. Again, before you try to do anything, can I factor? Doesn't look like it. I don't know any way to factor this. I don't know. Grouping doesn't work. So nothing I know works. So we're going to try P over Q. All right, what are the plus minus P factors? Well, which number is P? Huh? -2? Yeah, -2. So what are the factors of -2? 1 and 2. Okay, so then we're just going to do plus minus 1, plus minus 2. All right, let's look at Q. Q is the leading coefficient. What number is the leading coefficient? 3. Okay, so what are the factors of 3? 1 and 3. So then it's going to be plus minus 1, plus minus 3. Okay, so this is plus minus P over Q. And I highly recommend that you just have a system of doing the fractions. So what I usually do is I start with the first P, and then I link it to the 2 Q's. And I start at the second P, and then I go to the 2 Q's. That way I don't miss one of them accidentally. So plus minus 1, plus minus 1/3, plus minus 2, and plus minus 2/3. Okay, so how many possible rational zeros are there? Huh? 8, correct. How many could I actually have in this whole polynomial? 3. So then that means 5 of them doesn't work, or all 8 of them don't work. We don't know. So we're going to have to start by guessing. Huh? Yes, I always start with the lowest number and see if I get lucky. So try 1. See if it works. All right, f of 1 is equal to what? 0. So that means that's a 0. That's great. What should we do next? There are 7 other ones. Huh? Try 2? Okay, I'm going to tell you a fast way. Since 1 is a 0, we're going to factor it out. Right? That way we don't check the remaining 7 and figure out, ooh, nothing works, or oh, only 2 other ones work. We want to just utilize that 1 is a factor and use synthetic division and divide it out. So then we don't waste a lot of time. Okay, so synthetic division is a way of factoring out that factor. Long division is also the same idea. It's factoring out that factor. That way we reduce this polynomial to 2 degrees only. Okay, so let's do synthetic. We should get 0, right? Because we already checked. We should get 0. So 7, 7, 2, 2, 0. Okay, we do get 0. Now, if we rewrite this as a polynomial, we would get 3x squared plus 7x plus 2. What should we do at this point to try to find the other 2 zeros? Factor or quadratic formula. Okay, so now that we got to second degree, it's very easy. There's so many different ways we can solve this problem. So go ahead and find the other 2 zeros. All right, so what did you guys do? Quadratic formula or factoring? Factoring? Oh, okay. If you factor, what are the factors? Okay, so then the 3 rational zeros are 1, minus 1/3, and minus 2. Good. Okay, next we're gonna learn this new thing for predicting. Okay. What did I do? So this is called the upper and lower bound test for real zeros. So if we want to test to see if two numbers are the upper and lower bound of a function, okay, upper bound x minus k, where k is a positive number. Okay, so let me just read this whole thing and then you can fill it in and I'll explain what it actually means. Must be an upper bound if the last line of synthetic division is non-negative. So that means plus or 0. So non-negative, as long as it's not a negative number. Lower bound x minus k, where k is a negative number, must be a lower bound if the last line of synthetic division is alternately non-negative and non-positive. Oof, okay, what does that even mean? Okay, so what it means is that if you have this test, you're trying to figure out, let's say someone give you two numbers, and they said every single zero that is possible in this polynomial is contained within these two bounds, where the upper bound is a positive number, the lower bound is a negative number. If you want to test so basically they're saying, I give you two numbers, if there are possible zeros, it must be within here. Meaning outside of here, there is no way it's going to go through the x-axis again. Does that make sense? No. Okay, let me draw a picture. Okay, so they're saying that, let's say you have a function like this, and they give you two numbers. One here, one here. Let's say this is -2 and this is 3. They're saying that -2 is the lower bound, 3 is the upper bound, meaning all your zeros is now contained between those two numbers. Yeah? Okay, so that's what upper bound and lower bound mean. They said if you want to check to see if this truly is the upper bound, truly is the upper bound means that if it's a false upper bound, it will go down again and cross the x-axis. Yes? Okay, give me some feedback. Like yes, no, no. Okay, so we're testing to see if that number they gave us is a real upper bound or not. To be an upper bound means that after this number, it's never going to cross the x-axis again. If it's a fake upper bound, that means after this number, it will cross the x-axis again somewhere. Okay, so to test to see if that number truly is an upper bound, it has to fit these requirements. When you do the synthetic division using that number, you're going to see the last line of synthetic division has to be non-negative. Let's just try that first. Okay, prove that all the real zeros of this polynomial must lie in the interval -2, 5. Let's check upper bound. So they're saying that, I don't know how this looks like. It's a 4th degree, maybe like this. Oh, that's not 4th degree. 4th degree, maybe like this. It has to be stuck between -2 and 5. That's what they're saying. We have to prove that it's true. So let's check the upper bound first. Upper bound in this case, they said is 5. So we're going to check 5. They're saying that if it truly is an upper bound, if we put 5 in the synthetic division, so let's divide it out. Okay, 2 minus 7 minus 8, 14, 8. If we put it into the synthetic division and we do the synthetic division. So let's do this. 2, 10, 3, 15, 7, 35, 49. Oh, it got really big really fast. 245. Yeah, yes, I think. Okay, and then 253. I think this is right. Unless I did my math really, really wrong. Okay, so they're saying that if 5 truly is an upper bound, then you should look at the last line, which is this line, and they should all be non-negative, meaning you either see a positive number or a 0. So positive, 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 positive. So is 5 truly the upper bound? Yes, according to this. And then we're going to check on decimals to see if it's true. Okay, let's check the lower bound. Lower bound, they said, is negative 2. So let's do the same thing. Do a synthetic division check. Okay, so 2 drops down, negative 4, negative 11, 22, 14, negative 28, negative 14, and 28, 36. I think that's right. Yes. Okay, now we just look at the signs. Positive, negative, positive, negative, positive. So they said if negative 2 truly is a lower bound, then when you do the synthetic division, you should see alternately non-negative and non-positive. So do I see alternating signs? Yes. So then negative 2 is a lower bound. Okay, let's check decimals. Okay, so we did prove it. So then negative 2 and 5 are the upper and lower bound, or lower and upper bound of this polynomial. All right, let's have you try one. Prove that negative 2 and 3 is the interval for the real zeros of the function, blah, blah, blah. So you had to check negative 2, is that the lower bound? Check 3, is that the upper bound? Go ahead and do that. All right, what you guys get? Is negative 2 and 3 the lower and upper bound? Yes, so. Lower and upper bound.